So we use the digital twin that you can see on the right side. That is epsilon model from where we calculate the heat transfer coefficient, and then how efficiency is being calculated of the heating surface. Just I will show you a small thing. This is my digital twin. This is my furnace. So if I will double click it, so of course, when we model a power plant, generally we put all the geometrical data, and with the process data and the geometrical data, we simulate the model. And from the operating data, we get the heat transfer coefficient. This is basically Ka. You can see this is Ka, heat transfer coefficient. So when I am having a clean heating surfaces, I must have a very high heating transfer coefficient, a high heat transfer coefficient. But when I am having a dirty surface, I must have a very low heat transfer coefficient. Please understand that the the efficiency or the dirtiness completely depend upon the heat transfer coefficient of that surfaces at that time. So from this digital twin, generally we find out that what about the condition of the heat transfer, because generally we, as we know that we are having the convection heat transfer and the radiation heat transfer in the first pass, and we are having only the convective heat transfer in the second pass. So both convective and radiative heat transfer is being taken into account for this furnace, and then we calculate the heat transfer coefficient. So one of the thing is that we use this digital twin to calculate the heat transfer coefficient. It helps us to find out that whether my surface is really dirty or my surface is not dirty, and accordingly we take the decision that yes, we do the soot blowing or we don't do the soot blowing. So efficiency of the surface is completely on the basis of heat transfer coefficient. Now I will come to my module. Then efficiency of the heating surface we got. Then we got the flue gas temperature profile, flue gas mass flow. Then we get the boiler efficiency. Then we take the excess air. Then we take the air heater, leakages, exit temperature. So these are the criteria that is being taken into account. And then we see that if we don't do the soot blowing, then definitely my soot blowing cost will be less. I am having only my, just a moment. Yeah, sorry. So if I don't do, I am having a fixed cost. So if I don't do the soot blowing, then definitely my fixed cost will come down. But on the other hand, because of falling, I am having the losses. So because of the falling and all, so my cost will soot blowing. I will do the soot blowing, and my because of the soot blowing, my costs of soot blowing will increase. So one side, if I don't do the soot blowing, definitely I am having less my fixed cost. And if I will do the soot blowing, my fixed cost will increase. Yes. So, but I have to find out the optimal one so that I will do the soot blowing only when I am having my heating surfaces dirty and required. And this will be only possible with the help of my digital twin with my AI model, because this AI model will help me to find out whether my surface is dirty and as I told you, the heat transfer coefficient against my reference heat transfer coefficient. So reference heat transfer coefficient we find out with the help of neural model. We put all the heat transfer coefficient into my neural model. And as I told you that neural model is having the input layer is having the hidden layer and on the output layer, and accordingly it works, and we are having the output, and we try to give the weightage and all, and try to minimize the error at the end at the output, and accordingly we try to find out a very correct heating surface efficiency. So heating surface efficiency, time criteria, all the other criteria is being taken, and accordingly we tell you that whether the surface is dirty or not dirty, whether you go for the soot blowing or not soot blowing. So you can see these are the water wall, then another superheater area and all. And based on the fuzzy logic, based on the AI model and all, we recommend you that whether your surface is dirty or not dirty, and when you do the soot blowing. Because when your surface is not dirty and you are doing the soot blowing, definitely it's a cost. So I hope that this is the some of the case study that you can see that when my soot blowing is done, my heating surface efficiency is getting increased. And yes, these are the benefit that first thing is, of course, we are having the reduction in the steam. We are having unplanned shutdowns, prevention of unplanned shutdowns, prevention of damage due to the falling of the chunks of the of the slag, and improvement of the boiler efficiency and heat rate. So ultimately, we shall be able to save the steam, and we shall be able to increase the boiler efficiency, and we shall be able to improve the heat rate. So yes, we are using this AI technology, digital twin technology for my boiler cleaning management. So I hope I able to clear your this module. So first I have shown you data validation system, and second this uh, boiler cleaning management. So if you have any question or anything, you can put on the chat box so that we can discuss at the end. Now, one of the module I am going to tell you is statistical process control. So what is this module? Because basically AI and ML right now, many of the companies, of course, we are also doing stack. So we are using it for predictive analysis, especially for rotating equipment. Let us suppose we are going to have the ID fan vibration monitoring, or let us suppose we are going to have the bearing temperature or the turbine vibration monitoring. So generally, all the rotating equipment, or let us suppose vacuum also we are monitoring. So we can say that we are using this AI ML technology for predictive analysis of the fault well before the fault occur. So what is this technology, and how the data is being used? Of course, as I told in very early, that we require data. We require a DCS system. We require a database system so that all the data will be stored over there. And then once we are having the data which will be required to make the model, and then any of the module can be prepared and then analysis can be done. So this is just I'm showing you that the graph here you can see. So here you can see that this is the red line, brown line. This is the DCS limit of bearing temperature. So we are having the bearing temperature, you can see, and the light one is the noise, and then we are having some dark one. I'll come this. So this is the limit of your bearing temperature in the DCS system. In the DCS system, you are having this alarm. Now, through SPC, the bearing temperature is increasing. You got to know well before the alarm, DCS alarm. Here you are having the outage, and miss on the right dot, you are having the outage, and then you are having the, of course, you will have to do the maintenance job. But in the starting, if you will be able to know that the bearing temperature is increasing, then you can see that you are having the scheduled maintenance during that time. So you can avoid this outage. You can avoid, because the SPC, or you can say predictive analysis, it will give you the alarm well before the well before the real problem occurs, well before the shutdown, real alarm. So it avoid unplanned maintenance downtime. This is one of the very important criteria. Maximize asset performance. So how it does. So let us suppose this is the sensor data. You can see this is the sensor data. What we do, we are from left side, you cannot predict any fault. This is just the raw data. You'll have to apply some modeling tool, some AI model you have to develop. So here you can see that this is the neural model. So what we can do, we shall input this raw data into my neural model. And I will try to train the data. And I try to develop a reference data from this neural model. So this light line is there, and there is a dark line. So this dark line is basically my reference, or you can say my KPI. So we can see that from this dark line, how much there is a deviation. This dark line is my reference, and this I have developed. I have taken it from my neural model. Then I will take the KPI. I will have my actual versus reference. I will see where I am having a deviation, and then I will catch that, yes, from this point, I am having a lot of deviation. I will develop different charts. I am having my X bar chart, we are having my QSUM chart, UMA chart, and then I will catch that, yes, my bearing temperature, because from first sensor data, you cannot recognize that, yes, there is a fault. But of course, when you are having the fault, you will have to develop model, you will have to create the reference data, and then you'll have to create the KPIs, and then you can catch. Yes, there is a problem here. You can catch the things, and you can find out, yes, here is the problem. So here you can see that how we are using neural model. I will show you some of the cases also. Just a moment. So of course, what is the main use of this early detection of the fault? Because right now, this early detection of the fault, or this, you can say predictive analysis, it is being used by the STAG also, by our parent company, Iconi also. And yes, we are using it in our German plant also, and we are using it for our Indian plant also. So one of the things is that, yes, of course, you cannot monitor. Let us suppose you are having 5,000 data points. You cannot monitor. But from this technology, we condense the data from 5,000 to 1,000 and then 100, and which is very critical. And then we create the KPI, and then we shall give you alarm with respect to message, email. We can give you the information in the chart, in the heat map and all, that yes, there is a fault well before the fault. Well before the fault, and that, yes, some anomalies is going to happen. It is happening and it will happen after 1 month. It is predicted because of the behavior, because of the data conditions and all. Yes. Some more thing I'd like to show you that this is the vibration. Yeah, generally in a plant, you don't monitor for a month or for a year. Generally in the DCS system, you monitor for some small time. So let us suppose this is the real case study I'm showing you, that these are the two vibration sensor of FD fan. So you can see that this is the vibration sensor 1 and 2. I can see right now there is no problem. It's a very good. After in June, it is also good. August, I don't see any problem. September also, this is the condition. October, but if I will plot for a year, then you can see, that yes, the sensor one, you can see that the behavior of vibration of the sensor one, it's increasing as compared to two. Because when we are condensing the data and we are seeing it, here we can see, just a moment, and here is the catch. Here is the catch from SPC, that well before the fault, that by October 24th, here the data is from March to February, and my predictive analysis tool from the artificial intelligence, from the neural network model, we are able to find out my fault on 24th of October, well before my fault. So yes, for any of the predictive analysis, just I wanted to show you that we require a digital twin. And yes, we require the we require the data. Data is must, and then we can find out the trend recognition and all, and then we can catch. Because from the raw data, we have seen that we cannot find anything. We shall have to develop the reference. We shall have to develop the KPI, and then we can find out that where the deviation has started. And definitely we shall be able to catch that, yes, this is the condition, and here we are having the fault. So yes, these are the some examples where we are having this early year. So here in the right side, you can see we have developed the KPI and we find out the fault. And here the fault will be very clear, because we are having the actual value. And you can see that reference, how we shall get reference. A neural model will work, or my digital twin will work to give us the reference. And once we are having the actual and reference, then we shall develop the KPI. And then from the KPI, we shall catch from where abnormality has started, from where we are having the abnormality. And then accordingly, we shall catch the fault. So this is the basic concept which I wanted to give you, that how my AI ML model we are using for the predictive analysis. Of course, at the back end, we are having a lots of work which we do. But the concept is this, that I need a digital tool. First thing, I need a data. I need at least 6 month data to train my model. And once my model is trained, then accordingly it will give me the information time to time, that where I am having the fault. So of course during the starting I need 6 month data, so that I will be able to develop a very good model, very good neural model. And from the digital twin, with the help of digital twin neural model, we must have a KPI. And then from the KPI, we shall use the statistical method, and we shall have different charts and all, and we shall be able to capture the fault. And once the fault will be very clear, it will not be a wrong fault. It will be a correct fault. So this is the flue gas, the air preheater, gas preheater fault, which is there are some case study. And yes, let us suppose in a plant we shall choose 20 equipment. That yes, we want to monitor 20 equipment. Let us suppose we shall monitor the vibration of HP, IP, LP turbine. Then we shall go for the all fans bearing temperature vibration. Let us suppose ID fan, FD fan, and whatever is my priorities, I will monitor 30 KPI. And those KPI, I will, I cannot see or every time. So I must have a cockpit. I must have a heat map where I can see that yes, these are the three equipment where I am seeing some fault. So 20 KPI, and then alert will go by my email, by mobile and all. So that's why predictive analysis that is very right now it's in very much demand, whether it's a refinery industry or it's a power industry and all. Of course, we are using AI ML technology for this one and for this predictive analysis. So here you can see that feed water pump cleaning system. Of course, the concept is same. We are having, you can see light blue color. We are having a lot where we cannot find the fault. Of course, we filtered, we trained the data, we find the KPI, and then you can see in the right graph how much is clear that yes, this is the fault. Then air flue pressure drop in the air preheater. Here you can see that yes, the pressure drop in the air preheater from where it is being increased. Of course, flue gas pressure drop in the air preheater is always a problem in our power plant also. So here we can capture that yes, from which time my flue gas pressure drop is being increased and what action should we take during my maintenance period so that there will not be any outages, unplanned outages basically. Then exhaust system temperature also, there are some examples for the HP turbine that when it deteriorated, steam temperature and all. Then this is my condenser vacuum that when my condenser vacuum deterioration has been started. So I am having, of course, I will take vacuum, I will take CW flow. So many parameters I will monitor for my condenser. I will take CW flow, I will take CW inlet temperature, I will take the vacuum, I will take the saturation temperature. So all the data I will try to take and put it into the model, and then I will be able to check the KPI. I will see the actual value, I will see the reference value, and then from the neural model and all, I will develop the KPI and I will see that from which point the deterioration, the vacuum deterioration has been started. So there are so many examples which I wanted to show you. Of course, I am having today less time, but I want to give you some concepts that how it works. So hopefully this is clear to you that how AI is being used for predictive analysis. Of course, one is data, and another one is filtering of the data, neural model, digital twin, KPI, then a statistical process method to find out where I am having the fault.